We're going to take a look at operations, addition, subtraction, multiplication, and division with radical expressions. At this point, you've already done the simplifying of radical expressions. So let's get straight to it. Let's look at adding and subtracting radical expressions. So this might be enough to tell you what's going on right off the bat. This plus this equals that. Now the way you can think about it, if that's not clicking for you, treat this like a variable. If I said 4x plus 6x, your answer would be 10x. Well, the square root of 7, as long as they're common, meaning they're the same in each term, is just going to sit there like the x sat there. Same thing with subtraction. We have the square root of 10 in both of those, so it's just going to sit there and act like a variable, kind of like 6w minus 8w is minus 2w. So the square root of 10, as long as it's common to both terms, just sits there, easy peasy. Now in this example, you have to start doing a little bit of thinking because you notice I have a square root of 6, then we have a square root of 2, then we have a square root of 6. I would say that these two you can consider like terms. You can consider this to be like a 5x plus a 3y minus a 12x. If you had this situation back in your old-fashioned algebra days, you would put these two terms together. Likewise, these are like terms, so I'll put these two together, and this one will just come along for the ride. A 5 minus 12 is negative 7, and there you have your simplified radical expression. One more twist on this. If you look at these two, they're not common, so you can't put them together. But in this case, you can do a little bit of the simplifying that we've done before. If you think about the list of perfect squares, none of them will divide into 10, so I'm going to leave that one be. But 4 times 10 equals 40, and 4 is a perfect square. That means it gets to go to the outside as a 2. By doing that, the 10 stays inside because it's not a perfect square. This whole thing turns into 10 square roots of 10, which is nice because now I have common radicals. This 2 square roots of 10 never changed because there was nothing I could do. Now if I just think of this as 10x plus 2x equals 12x, and I do the same thing with square roots of 10, I'm done. So what we've covered here so far is the adding and subtracting of radical expressions. Now we're going to take a look at the multiplying and the dividing. When you're multiplying radicals, you can just follow these two guidelines. Multiply your coefficients and multiply the insides of the radicals. So the 6 and the 10 are the coefficients. They multiply to 60. The 2 and the 7 are inside the radical. 2 times 7 is 14. I'm done. I would look to see if I could do any reducing. In this case, I can't. In this next example, the 3 and the 8 are inside the radical. Technically, there's a 1 on the outside of both of those radicals, but 1 times 1 is 1. So multiplying the coefficients, not a big deal in this case. 3 times 8 is 24. That's a good answer, but it's not a final answer because remember the square root of 24 can be simplified. When I think of the square root of 24, I go back to my list of perfect squares. Is there a perfect square that divides perfectly into 24? And if so, what's the largest one? In this case, 4 divides into 24, so 4 times 6. Same thing as 24, but 4 gets to go to the outside as a 2. Okay, and finally onto dividing the radicals. Similar idea with the multiplying. Since we're dividing, we're going to divide or reduce the coefficients, and we're going to divide or reduce the insides of the radicals. In the first example, remember when there's no coefficient on the outside, it's really a 1. So a 1 over 1, there's nothing to reduce. Now here's the deal. When I've got the 20 and the 10, I have to divide or reduce the radical insides. So I can think of the 20 in the numerator and the 10 in the denominator as a numerator and denominator inside the radical. Now, what would you do with the 20 divided by 10? Well, that's just a 2. And now there's nothing else to do. That's your final answer. We'll go to a slightly more complicated problem, and these 2 bullet points might make more sense. Don't look there yet. So I look at this problem and I say, oh, I've got coefficients on the outside. Well, 12 over 6 reduces to a 2 over 1. Now I have a 40 and a 10 in radicals, so I need to think about that. And when I do this, there's a good first step. The coefficients reduce. Inside the radicals, I can think of those being underneath one radical, which means I can take the 40 divided by 10 and reduce it or divide it. In this case, when I divide it, I get a 4. So I get a 2 square roots of 4. But by the way, square root of 4 is really a 2. So it's really a 2 times a 2. And finally, to end this video, I'm going to take this same problem and I'm going to rewrite it with slightly different coefficients. Up here on the bullet points, it says we divide or reduce the coefficients. So 12 divided by 6 gave us the 2, but you'd say, well, 8 doesn't divide evenly by 20, but you can reduce 8/20ths. You would say back in the day, what number divides evenly into 8 and 20? In this case, the best number is 4. 4 divides into 8 twice. 4 divides into 20 5 times. So I end up with 2/5. So 8 over 20 reduces to 2/5. 40 over 10. And now I'm just going to continue on. The 2/5 is going to stick. The square root of 40 over 10 is the square root of 4. And the square root of 4 turns into a 2. Now I can multiply the 2's in the numerator. There's really a fake, not a fake, but a hidden 1 denominator. And my final answer is 4/5. We did this example to show you that you don't always end up dividing the coefficients to get an integer. Sometimes these coefficients reduce to a fraction. Okay, this has been the operations with radicals: addition, subtraction, multiplication, and division.